joined IMSc, and she was also a faculty at Chennai Mathematical Institute, Inspire faculty at Chennai Mathematical Institute. She then joined IIT Madras, and where she is an associate professor now. Her topics of interest are mainly quantum error correction, quantum cryptography, and foundations of quantum mechanics. Today, she is going to talk with us about noise adapted quantum error correction and fault tolerance. And we'll all welcome Professor Prabha to give the talk. Prabha, it's over to you.
Yeah, thank you, Chandra, and thank you to Professor Prashanta Panigrahi and the organizers for having me as part of this school and workshop. We all know that QIQT has now become a regular feature of all our annual calendars, and I'm sure the students are eagerly looking forward to this very comprehensive school and workshop. I'm very happy to be a part of this. As Chandra rightly mentioned in introduction, quantum error correction is one of my primary research interests, and it has been so for some time. So in this talk, I know this is part of a school and workshop, so I have tried to also introduce some basic ideas of quantum error correction. Of course, it will not be like a tutorial, so you will have to then maybe look up some of the references to learn more, but I will try to keep it as self-contained as I can. And of course, the latter part of the talk will be about my own research over the last 2-3 years on this topic of noise-adapted quantum error correction. Okay, so without further ado, let me begin. All right, so like I said, I will try to introduce these ideas of decoherence and quantum channels. I will talk about what today we call as general purpose quantum error correction versus channel adapted or noise adapted quantum error correction. I will use the terms channel adapted and noise adapted interchangeably. So I mean the same thing when I say both. So you will find that in my slides, I use both terms. Okay. So with this preliminary, then I will try to motivate what is the challenge of doing quantum error correction in today's era of noisy quantum devices. And in particular, I will talk about this problem of noise adapted quantum error correction. And I will present a recent solution that we came up with to find good quantum codes which are tailored to specific kinds of noise or errors. Okay. And then I will move on to talking about something which is more maybe advanced or more technical, namely the idea of fault tolerance. So the quest for a robust and scalable quantum computer doesn't stop with quantum error correction. There is a need to then implement all these error correction circuits and things that I will show you in so-called fault tolerant way. And I will try to explain what that is. And I will also, again, give you a brief glimpse into our recent work on how we can achieve fault tolerance with quantum codes of shorter length or using fewer qubits. Okay. And then I will conclude with a summary and future outlook. I'm not sure how much of the last part I will get to do. I know I have about an hour. So we'll see how it goes. Okay. Maybe around the halfway mark, I will stop for some questions so that the students and the audience does not get completely lost. In case you've already heard me talk about this before, my apologies. I may have spoken about this recently in the Quest Symposium and all that. But yeah, if you're new, then hopefully you will enjoy the talk. Okay, so today we are in an era of so-called NISQ devices. I'm sure there are several talks in the school which have mentioned this terminology. So these are noisy intermediate scale quantum devices, right? The devices that we see companies like Google and IBM and IonQ and Xanadu. So we now have a plethora of companies that are making quantum bits from different architectures. And they're all showcasing devices with about 100 qubits today. But these are all noisy qubits. And we call them intermediate scale quantum computers or quantum devices because they are still not to scale, right? They're still not at a stage where I can run a short factoring algorithm on a 200-digit number and get you the prime factor, right? We are still not there yet. But they are genuine quantum processors nonetheless. So these are the two issues. One is noise and the other is scalability. They are noisy and they are not yet scalable to be truly universal quantum computers capable of achieving this quantum advantage that everyone talks about. So the noise in quantum bits and in quantum gates poses a serious challenge in actually realizing the true potential of these quantum devices. So there's noise not just in the implementation of the qubit, but also in how these quantum gates or quantum operations are realized, right? And of course, the reason that we still think quantum computing is a very feasible goal, even practically, is because of ideas from quantum error correction, which at least theoretically shows us that it is possible to do error mitigation. It is possible to overcome the effects of noise. And second, that it is possible to indeed scale up these devices to truly universal quantum computers, right? So what is recoherence? And perhaps you have had lectures or you will have lectures on this idea of open quantum systems. So the typical quantum mechanics that one studies in even in a graduate level course is all about closed quantum systems, which are all evolving according to the Hamiltonian in a unitary fashion, right? But what happens when I have this? So are you able to see my pointer moving? Chandra, are you able to see the point?
Yes, yes.
Okay, fine. So this HS is what I call the system Hilbert space. And typically this system is not isolated. It is interacting with this so-called environment or bath. And this is what we call H sub E, the E denoting that this is the Hilbert space of the environment. And these system and environment are interacting in a unitary fashion, right? They are interacting according to some interaction Hamiltonian. And the overall evolution of system plus environment will be unitary. Because the system together with the environment can be thought of as a closed system. That is a reasonable physical statement to make. And so together they will evolve unitarily according to some unitary operation, which I've just called UFE. But you see, as an experimenter who is building these quantum bits and trying to generate specific quantum states, I am only concerned about the system. And the environment is typically a much larger system, although I have drawn this box bigger and this one smaller. The environment is typically a much larger system with many more degrees of freedom, which the experimenter cannot control in his or her lab, right? And so since this is a much larger system, we want to find a way to describe what happens to just system alone when it is undergoing this kind of unavoidable interaction with the environment. And the mathematical model of how the system alone evolves in an open quantum system scenario is what is called a quantum channel or a quantum noise channel. Because what you need to do is you need to take this unitary action on the system and environment together and then trace out the environment degrees of freedom. Because these are the degrees of freedom that we actually don't have control over. Oftentimes, we may not even be able to measure the environment with any reasonable degree of accuracy. It is the system that we have control over, right? And the system that we can measure, that we can characterize, that we can do gates on, etc. So this map is what we are interested in. What happens to the initial density operator rho of the system after it interacts with the environment like this? It changes to something called E of rho, where E is the map that is representing the system evolution alone in this kind of an open quantum system scenario, right? So this system state alone will typically lose coherence because this evolution is not unitary. What is unitary is the larger system bath interaction. If you trace out the bath, what you're left with is a certain map, which is called E. I'll explain what this map is a little bit. But this map will typically not preserve coherence. It will not preserve purity. So the system loses coherence. There is dissipation, right? And this so-called unwanted interaction is not something that is under our control. And so this is what is noise for quantum states or quantum bits, qubits, right? So this is modeled typically as what is called a completely positive trace preserving map, right? So this is, I said this in words just now, that I have this unitary action acting on system state, but this unitary is obviously not just acting on system, it's acting on system and environment. So let's assume that to begin with, the system and environment were not entangled, right? They are in what is called a product state. And then after the action of this system bath unitary, you trace out the bath or the environment, and what you're left with is purely a state of the system. And this state can be realized as the action of a certain kind of map on the system state, and this map has a certain mathematical property, and that is that it is a trace preserving and completely positive map. So for the purposes of this talk, I will not get into what complete positivity is, etc. Maybe there's a different lecture that you have on open quantum systems and so on. But let's just understand that there is a certain mathematical model of a map that describes the system state as it decoheres or loses coherence because of the action of, because of interaction with the bath or environment. Okay. Right. So what is this quantum channel? It is, as I said, a particular kind of map. It turns out that this kind of a map has a very simple description in terms of a set of operators which are called Krauss operators. So the state of the system alone changes according to E of rho, right? So E of rho is essentially the final state, the noisy final state after the action of system bath or system environment interaction. And this final state can be realized from the initial state rho as sum over I, EI rho, EI dagger, where EI is a set of any set of operators on the system Hilbert space. These are called Krauss operators. And what makes this a physically valid map is this property that when I sum over the EI dagger, dagger is the transpose conjugate action. So EI dagger, EI together must sum to identity. Okay. So this is what is called a operator sum description, right? So what you have managed to do is you have managed to describe the system evolution alone, although it is not a closed system, although it is not an isolated system, you have managed to describe the system evolution alone in terms of a set of operators which act only on the system. These are the Krauss operators, and the complete state after the interaction with the environment can be described as sum over I, EI rho, EI dagger. The EIs need not be unitary operators. They need not be Hermitian operators. They need not be any specific kind of operators. The only constraint that they need to satisfy is this, that when I take the adjoint of every operator and multiply with itself and sum over all the operators, that should sum to identity. So there may be some number of Krauss operators that describe a given channel. I'll give you some examples now. This could be 2, this could be 3, this could be 4. We will see different kinds of examples of such quantum channels now, right? So how many Krauss operators there are to describe a channel comes from the physics of the problem. It comes from the nature of the system environment interaction and so on, right? But this is an abstract description, what I've written here, which takes care of any kind of open quantum system. The only assumption, there are two assumptions we make. One is to begin with, system and environment are not interacting. They are in a product state. And second, the evolution of system plus environment is unitive, both of which are reasonable physical assumptions to make. Okay. So here's the first example of such a quantum channel. This is probably a system that many of you are aware of already. It's a 2-level atom or any 2-level system that is in a cavity. So it is interacting with the radiation modes of in the cavity, it's interacting with the cavity mode, right? And this could be interacting, for example, via the well-known Jaynes-Cummings interaction. Again, I will not get into the details of the Hamiltonian and so on, but it is a reasonably simple exercise to take the Jaynes-Cummings Hamiltonian and assume that you are dealing with a 2-level atom or a 2-level system. There's a ground state and there's an excited state. Assume that the environment, though it may be an infinite set of radiation modes, because it's a 2-level system, it may at most interact with only 2 levels, let's say in the fog basis, right? And then you can write down the interaction Hamiltonian, you can get the unitary map, and then you trace out the cavity mode. Then what you will get is a map that is purely acting on the system, the 2-level system, and that will model this dissipation, this spontaneous decay of the 2-level atom. So what happens with this 2-level atom in a cavity? When it is in the excited state, it can undergo a spontaneous transition to the ground state with the emission of a photon, right? So this is the physical process you're trying to capture, and the way it captures it is using these two Krauss operators. So in this case, there are two Krauss operators because one way to think about it is because there are two possibilities. Suppose your system was in the ground state, nothing happens, right? There is no, the interaction with the environment does not cause any disruption if it's in the ground state. The ground state is a stable state in this model, in this interaction. That's what we often call a fixed point for a map, right? So the ground state is like a fixed point for the map. So that is what the first operator is capturing. I hope everyone is familiar with this outer product notation, right? So this is the 0, 0, nothing happens to the ground state. Now, when you're in the excited state, which I call Ket1, right? So Ket0 is my ground state and Ket1 is the excited state. When you're in the excited state, one of two things could happen. Either you continue to remain in the excited state, and there is a certain probability with which that will happen. And that is what this term is capturing. The second operator, E1, is actually capturing this decay. This is actually capturing the decay from the excited state to the ground state. And there is again a probability associated with that. And this probability is what we call gamma. There is a square root because you notice that in this operator sum representation, everything is acting by conjugation, right? We are describing the action on a density matrix. So everything is happening by conjugation. So that's why there's a square root here. And when once it acts by conjugation, the factor gamma comes out, right? So this gamma is basically the physical parameter which captures the probability with which the excited state will decay to the ground state, okay? And I have put here T1 coherence time, but unfortunately I have not put the expression here. This gamma actually has an exponential decay with time. You assume that you have prepared this two-level system in the excited state, let's say to begin with, somehow you shine some light, you do something and you take it to the excited state. Let's say that's time 0. What happens with time, right? The longer that this two-level atom is left to interact with the cavity mode, the more probable it is that this excited state will decay to the ground state, right? That its energy dissipation will happen to the cavity mode. So this gamma then starts off as being maybe 0 at time t is equal to 0. And then as time increases, the gamma tends towards 1, right? So the idea is if you wait long enough, your Ket1 state is going to come to the Ket0 state. But typically, when I'm doing a gate operation, I'm somewhere in this intermediate time, right? I'm somewhere at this intermediate time where with certain probability, the excited state may have decayed to the ground state, and that probability is an exponentially decaying function of time. So how do I model this intermediate state? And that is where this operator sum representation comes into play, that it is modeled as E0 rho E0 dagger plus E1 rho E1 dagger as indicated by this operator sum representation. So that's why the final state is in a mixed state. Even if I start with a pure state of Ket1, I will end up with a mixed state because with a certain probability, I will continue to be in Ket1 and with a certain probability, I will decay down to Ket0. And what is the time scale at which this is happening? That is what is captured by the so-called coherence time or T1 time. So the T1 time is nothing but this exponential function that I told you, it is the decay constant in this exponential time decay. Okay. All right. So this is just to give you a glimpse into the kind of coherence times that one is seeing in, let's say, superconducting qubits today. By the way, I should tell you that this kind of a model is a very realistic model of decay in superconducting qubits. Those of you who are maybe familiar with the IBM Q processors, if you go to any of the IBM Q processors on the cloud and you click on any of the qubits, the information that you will see about each qubit is it will tell you what are the so-called T1 and T2 times. And the T1 process is essentially exactly this dissipation process, which is modeled as the amplitude damping channel. So this is a very important decay model for superconducting qubits today. And these are the kind of lifetimes that you see. I'm not getting into what is T2. T2 is a different kind of noise. It's called phase damping, right? It's a different process. T1 is effectively amplitude damping process. And you see that today the coherence times, which are all in microseconds. So where are we? We are somewhere here, 2022. We are around 10 to the 4 microseconds. So essentially we are hitting the millisecond regime, but we're still not there, right? So this is today's scenario. So what does it mean? It means that within, let's say, a millisecond, there is a very high probability for the superconducting qubit to have decayed to the ground state or the zero state. Imagine you were in a superposition. Again, within a millisecond, there is a very high probability that the superconducting qubit would have decohered from the coherent superposition of 0 and 1 that you initially prepared. So then the question becomes, how many gate operations can you really do within that time, right? And that is the reason that today's quantum computers or quantum devices are not yet scalable to realizing their full potential, right? So that's just one example of a dissipation or a noise model, right? One can think of other examples of such decoherence models, and this is probably one of the simplest models that everyone may have already seen or encountered. This is the bit flip, right? The classic bit flip. It happens for classical bits also. There is a certain probability with which the 0 will flip to a 1, and a certain probability with 1 will flip to 0. There is a certain probability 1 minus p with which 0 will remain unchanged and 1 will remain unchanged, right? So now again, you notice that because of this probabilistic nature of this action, this is what we typically call a stochastic process, right? In physics also. The idea is it's not deterministic. It is not as if there is an X gate acting on Ket1, which is deterministically taking it to Ket0. There is not an X gate acting on Ket0, which is taking it to Ket1. Rather, it is like a probabilistic X gate. There is a certain probability with which the X operation happens, right? So that is this. There is a certain probability with which the qubit remains unflipped, and that is this 1 minus p. So even though the system may start out in a pure state, it eventually ends up decohering to a mixed state like this, right? So this bit flip channel is an example of what we call a Pauli noise, because in this case, the Krauss operator, what I call the Krauss operator, I denoted it as E0 and E1, is essentially sigma X operation, which is a Pauli operation. The other Krauss operator is simply identity, right? Similarly, yeah, so I have this exponential description here. This is what I was trying to say in the last slide, that this probability with which the noise occurs typically goes as an exponential function, right? And this exponential model, there's a reason why it's exponential. It comes from the fact that you assume that the underlying evolution is Markovian typically, but those are again details. We need like a full lecture on open quantum systems to really understand this behavior. But this comes from solving something called a master equation in open quantum systems, right? And once again, there's a characteristic time scale, which is what is called the coherence time, okay? There are other noise models, a phase flip channel, for example, where instead of sigma X noise, what happens is sigma Z noise. This is again a Pauli noise channel. Now you can imagine a scenario where you have, with certain probability, nothing happens to the qubit, right? With a certain probability, it's either X noise or Y noise or Z noise. And this is what is called a depolarizing channel. So as you can see, quantum states undergo not just one kind of noise or two kinds of noise, they can undergo an infinite set of noise maps, right? Depending on what the underlying physical process is, it could be a bit flip, it could be a phase flip, it could be depolarizing, it could be amplitude damping. And the nature of the noise channel is actually very different in each of these cases. Of course, these three channels listed on this slide have the commonality that they're all Pauli noise, but the amplitude damping, which I showed you, the T1 process that I showed you 2 slides ago, is a classic example of a non-Pauli noise, right? So this is one of the challenges of quantum error correction, that you have not just one kind of noise. So in classical bits, what can happen? The bit can either flip like this, bit flip channel, or the bit can get erased, which is called an erasure channel. But in the quantum case, you can have a whole continuous parameter, infinity of noise channels, right? And so how does one hope to correct for these different kinds of noise models? So enter quantum error correction. And this was what I have quoted here is a very nice poem by Daniel Gottesman, who's one of the pioneers of quantum error correction. His thesis is probably the first things that you would like to read on quantum error correction, where he says, with group and eigenstate, we've learned to fix your quantum errors with our quantum tricks. So yes, these quantum errors are challenging. There is more than one kind of quantum error, right? But then quantum mechanics also gives us a nice set of tricks using which we can handle these multitude of error models, right? So let me give you a simple example of an error correcting code now, okay? So what does one need to do to protect the quantum states against these errors? So let's say, for example, you know that the noise model that your qubit is going to undergo is bit flip, which means with certain probability, your bit can get flipped to 1 or 1 can get flipped to 0. So what would you like to do? Classically, you will take that single 0, and instead of a single 0, you will store or you will send 3 zeros. Instead of a single 1, you will send 3 1s, right? So the question is, can one do that quantumly also? Can you have a quantum repetition code, right? Because if you have a repetition code, then you know that so long as the noise probability is low, which means so long as p is small enough, typically you say p is less than half, then with high probability, it's only one bit that is going to get flipped out of the 3. Not all 3 bits are going to get flipped. So if I look at sets of 3 instead of single bits, I can do a majority count, and I can identify, first of all, whether an error has occurred. And second, I can know where the error has occurred, and I can accordingly correct first, right? So instead of 1 0, I send 3 zeros. Instead of 1 1, I send 3 1s. If I look at that set of 3 1s, let's say the middle one has become a 0. Instead of 1 1 1, I get a 1 0 1. Then I know that the middle bit actually got flipped, because it's highly unlikely that 2 bits got flipped, because this p is a very small number, much less than 1. That's the regime in which we would like to operate, right? So this is the classical repetition code. So what can you do quantumly? Can you do the same thing? Can I replace every ket 0 by 3 zeros and every ket 1 by 3 ket 1s? Of course, I can do that for a simple ket 0 and ket 1. But the whole advantage of doing quantum information processing lies in preparing superpositions like this, alpha 0 plus beta 1, where alpha and beta are complex quantities. So now if I have an alpha 0 plus beta 1, how do I implement this repetition code? Can I make 3 copies of alpha 0 plus beta 1? Can someone answer me in the chat, just so that I know that people are around? Can we make 3 copies of alpha 0 plus beta 1? Okay, so someone tells me no, and why not? Exactly. So thank you guys. So I'm glad to see people are awake and alive, and we have not all decohered yet. Good. So the no cloning theorem tells us that I cannot copy an arbitrary quantum state. So because the power of quantum computing lies in these superpositions, you would like the ability to encode. So this is what we call encoding, right? That in place of 1 qubit, you are now going to prepare or store or send multiple qubits. But we have to do it in a way that circumvents the no cloning theorem, right? Of course, I put the answer on the slide. I didn't realize that. But anyway, good to see the answers coming up. So, but the point is, again, quantum mechanics allows us a way to do this, right? And the way it allows us is by using additional qubits, which are called ancillary qubits, and by using multi-qubit gates, which are entangling, right? So this is the circuit that I have here. This is a circuit that captures the 3-qubit quantum repetition code, which is not about making simply 3 copies of an arbitrary state, but it takes alpha 0 plus beta 1 and maps it to a state like this, which is alpha 0 0 0 plus beta 1 1 1. And those of you who know a little bit about entanglement and so on will realize that this is actually an entangled state. In fact, if alpha and beta were both equal to 1 over root 2, this is a special kind of entangled state, which you probably may know of. What is it? If alpha and beta are both 1 over square root 2, what state is this? What is this 3-qubit state? Do people know the name of this thing? Exactly. Very good. It's a GHZ state. So this saying that you take a single qubit and now you represent that information in an entangled 3-qubit state. Okay. So this is basically what a quantum error correcting code is. It takes, so look at the circuit now. So there is this state psi here. This psi is this arbitrary state alpha 0 plus beta 1. The other 2 zeros are the ancillary qubits. And now look at what I have done. I have 2 C0 gates here from the first to the second and then the second to the third. And these 2 C0 gates are essentially entangling these 3 qubits, so that if I start with an alpha 0 plus beta 1, I'm sure you can work this out yourself. You will see that you get an alpha 0, 0, 0 plus beta 1, 1, 1. So then I have a box which says error. Okay, and this is where we are making a crucial assumption. And this assumption I'll try to address in the second half of my talk, assuming we get there. Okay, what we are assuming is that this process is all noiseless. Okay, this tie, this C0 gate, the ancillars, all of this is noiseless. Okay, and this is now where the error comes in. Once I have done this faultless encoding process, the error acts. Okay, and now I'm going to tell you how this 3-qubit state protects you against bit flip errors, because now I'm assuming that the error model is bit flip, right? So how does it protect me? Well, these two, so now notice what has happened is I've gone from a simple 0-1 space, which is a 2-dimensional space, to a different space, which is now a subspace of the 3-dimensional, 3-qubit space, right? So the 3-qubit space is actually 8-dimensional, right? So that's an 8-dimensional space, but I am only looking at superpositions of the form alpha 0, 0, 0 plus beta 1, 1, 1, which means I'm looking at the span of 0, 0, 0 and 1, 1, 1, which is essentially a 2-dimensional subspace of this 8-dimensional space. So this is a 3-qubit quantum code. Okay, quantum code is essentially a subspace of a larger Hilbert space into which you have decided to store your information, right? And the reason this is useful is, now notice that if I have a single bit flip, let's say on the first qubit, QET0 becomes a QET1, right? So it maps my 0L, the L stands for logical, right? Because although I have 3 physical qubits, 0, 0, 0, it's effectively 1 logical qubit. Although I have 3 physical ones, it's effectively 1 logical 1. And all my states are going to be superpositions of this logical 0 and logical 1, right? So if I have a single qubit which is flipped, then it maps the 0 logical to an orthogonal state. If I have a single 1 that is flipped, it maps the 1 logical to an orthogonal state. So distinct errors map my logical 0 and logical 1 to distinct orthogonal states of this larger Hilbert space. So that is what you gain by going into more number of qubits. You gain a whole lot of additional room in the Hilbert space. So now your errors can actually map your code space to distinct parts of this larger Hilbert. Once I have orthogonal states, again, the basics of quantum information processing will tell you that orthogonal states can be distinguished. You can perform a measurement to identify which orthogonal state your system is in. If it is in the state 100, I know that 100 was not originally in my code space. So I know that an error has occurred. And with high probability, it's the first qubit that has gotten flipped. So I will simply flip the first qubit back, and that's how I do the error correction. So that is what the second half of this circuit is doing. It is showing us how to perform these measurements without destroying these 3 states. Because you see, if I take the errored state, the state with error, the 3-qubit state with error, and I directly measure it, then it's again going to destroy the superposition. So I don't want to do that. That's again counterproductive. So again, I have this nice trick of using ancillary qubits. I have at my disposal nice gates like the C0 gate. So again, I leave it as an exercise to you to check that if I have this ancillary qubit 0 and I do these 2 C0s, depending on which of these qubits gets flipped, the 0 will either get flipped or it will not get flipped, the ancillary qubit. Similarly, this target qubit, this ancillary qubit becomes the target qubit, will again get flipped or not flipped, depending on whether the control qubit had an error or not. So essentially, you make these 3 qubits, which is where your information is being stored. These are called data qubits in the language of error correction. So you make your data qubits as the control qubits, and then you measure the ancillary. So the M here are essentially measurements, and they are Pauli measurements, right? You're measuring either a sigma Z or a sigma X typically. And then these 2 lines are basically classical controls. They're telling me that if I measure this ancillary qubit, I get classical bits out of that, right? Out of this measurement, I will get a classical 0 or 1, and I will feed that into this correct box, which will tell me whether I need to apply a corrective X gate or not, and on which qubit I should apply it to. Okay. So this is the summary of what I just said. I said that bits on different qubits are distinguishable, so errors can be detected and corrected. And I said that, well, there is a certain regime in which this code will work, and that is the regime when this probability is smaller than a half. The probability of bit flip is smaller than a half. And why is that important? Because if the probability of a bit flip is higher, then it's possible that I have multiple bit flips happening rather than a single bit flip. And then I will no longer have this property that each error is uniquely detectable and correctable. Okay. So let me just pause here for any questions. I think I see something written in the chat. So can this person speak up? Like, because I don't understand what you're trying to ask here. Oops. Sorry. Hello. Okay, so I just see a question in the chat which says, what if there's a 0, 1, 0 measurement? See, there are only two classical bits that you measure at the end, because there are only two ancillars, right? So you measure, you will either get 0, 0, you get 0, 1, 1, 0, or 1, 1. Okay, so there are four possibilities at the end, and each of these four possibilities will map back to either no error happened, or the first qubit got flipped, or the second qubit got flipped, or the third qubit got flipped. Okay, so these are the four possibilities, and you have four outcomes corresponding to those four possibilities. Okay. Excuse me. Any other questions so far? Any quick questions? No? All right, so let me continue. Okay. The error box is not something we designed. How is the error box designed is what somebody is asking me. The idea is that the error box is something that is actually happening to your qubit, right? Of course, if I want to run this kind of thing on IBM-Q, then I will implement an X gate, either in the first qubit or the second qubit or the third qubit. That's all the bit flip error is. It's just an X gate, right? So if you want to check this, that's what you would do. But the understanding is that this error box is something that is naturally happening to these qubits, right? Of course, it is happening from time t0, from the time you're doing the encoding. But for the purposes of ideal error correction, you assume that you somehow do this encoding in a noiseless way. And then as the noise acts, you are able to do this, all this, extracting the syndrome. You're able to do all these measurements where you extract the syndrome about the noise onto the ancilla, and then you do this measurement. Okay. Excuse me.
I have a question. So
yeah,
you are making it a 3-qubit system and adding 2 ancillas, and
yeah,
we want to retain the state of the psi, right?
yeah, yeah.
Oh, okay.
Exactly. See, finally, I have a 3-qubit state here after the correction, but that 3-qubit state will either be ket 000 or ket 11 or some superposition like this, right? Now, if you want to get back to the single qubit state, what do you do? Maybe that was your question. Well, how did you get to the 3-qubit state? You did 2 C0. That's a unitary operation, which can be reversed. So I simply apply this circuit in reverse, the first part of the circuit, which is the encoding circuit. I simply apply it in reverse, and then I will get back the information onto the single qubit state. That's all. So the encoding always has to be a unitary process, because when I'm taking the information from a single qubit to a multi-qubit space, I want to do it in a way that A, that preserves the coherence, and B, is reversible, because that's how I can get the information back to the single qubit state, right? Is there a finite probability that all 3 bits get flipped? Of course, there is a finite probability. It is just very, very small. So if P is the probability of a single bit flip, then what is the probability of 3 bits flipping? You know the answer. That's P cube, right? It's order P cube. So if P is much smaller than a half, then you can imagine that P cube is much, much smaller, right? That's why I said this P less than half is a kind of sweet spot. If your noise is too much, if you have super noisy qubits, then there's nothing you can do, right? But if your noise is reasonable, is within some threshold like this, then error correction can help you. Okay, I'll just take one last question. How can we implement the correct box in QIQT? Well, that's again just an X gate, right? Because what happens, one of these 3 qubits is going to get flipped. So once I identify which qubit has gotten flipped, how do I correct it? It's just an X gate, because the error is of the X form. The recovery is also simply the X gate, right? Okay, so let's proceed. This is just a more formal definition of what a code space is. It is storing, let's say that D0 is the amount of information that you would like to store, right? That's typically 2, because typically I'm manipulating qubits, right? So D0 is typically 2, and that is encoded into a 2-dimensional subspace of a larger Hilbert space. That becomes your physical space, and this subspace becomes the code space or the logical space. This is what I explained in the previous slide already. There is an encoding operation W, which is typically a unitary. There is a recovery map. In the previous slide, the recovery was simply, like I said, just doing an X gate. But now if you imagine that you have something like amplitude damping noise, which may be the true noise model, let's say on the IBM Q processor, then how do I correct for it? I can't simply make do with an X operation there. It's a bit more complex, right? And we'll come to that. And then, so this is the formal definition of a perfectly correctable error correcting code. We say that the C, this code space, is perfectly correctable if there exists a quantum channel R. So this quantum channel R is nothing but a recovery map. And like I said, in the case of the bit flip, this was very simple. This is what someone asked me, what is the correct box? Well, that circuit was simply applying X gates, individual X gates, right? But more generally, this recovery might have to itself be what is called a CPTP map, a completely positive trace preserving map, or a quantum channel. And together with the action of recovery plus noise, the idea is that every state in the code space is recovered, right? So if I have any state in the code space C, the noise acts on it, that is E. Then I do a recovery operation. After the action of noise and recovery, I should get back the initial. Now, this is, of course, a very stringent requirement, right? It may not be possible that you get back exactly the same state. So this idea of perfect correction is a bit of an idealization. So we can then go ahead and define something called approximate correctability, where we say that the action of a noise is approximately correctable if there exists a recovery operation such that after the action of noise and recovery, I get something that is close to the initial state, but may not be exactly the initial state. And that's what this approximate sign refers to. So now I'm trying to kind of deviate from the standard error correction procedure, which typically assumes perfect correctability. Instead, I'm going to talk now onwards about approximate correctability, okay? Because in the previous slide, what we did with bit flip noise was perfect, right? It was all, I perfectly distinguished the errors, I perfectly put them back. It's all perfect correctability. So here is a bit of a cartoon representation of what I was trying to say with the 3-qubit code. The 3-qubit code is like this little box sitting inside a larger Hilbert space, right? This little box is a 2-dimensional subspace of a larger Hilbert space, right? And these errors are mapping the code space to different parts of the 3-qubit Hilbert space. And this is what I was trying to say. They're mapping them to disjoint parts, non-overlapping parts. And that is why I could then measure this larger 3-qubit Hilbert space at the end, identify whether it was error E1, E2. So E1 could be the case where there is no error at all. E2 could be the case where a single bit got flipped. E3 could be the case where the second qubit got flipped. E4 could be the case where the third qubit got flipped, etc. Right? So all of these are now disjoint, distinguishable. So once I make that measurement, my recovery operation is very simple. I simply have to do an appropriate X gate at the location where I have detected the error. So this is the mathematical understanding of a perfectly correctable code. But in practice, this is what is going to happen, right? So what I have drawn here is actually not fully an approximate code. I didn't realize it. So first of all, these boxes could actually be overlapping, okay? And what is more, so what I've done here is the code space itself has not gotten deformed. Why? Because the noise, which is the Pauli noise, is essentially just unitary noise, right? An X noise or a Y noise or a Z noise, they're all unitary gates. So the noise itself is just unitary. So it doesn't deform the code space. But typically, first of all, the noise need not be unitary. Secondly, these different boxes could actually be overlapping, right? That's what indeed happens in the case where the noise is amplitude damping. Because amplitude damping is not of the Pauli type. There is no identity part in the Krauss operator. There is no X, Y, Z part. Instead, I have these two operators, E0 and E1, which are not unitary. So they will deform a typical code space in random ways, and they will lead to overlapping subspace. Okay. And what approximate correction tells you is that even in such a scenario, it may still be possible to detect and correct up to a certain extent. And that is what the idea of approximate correctability is. Okay. So before I move on to that, I just want to motivate this idea a little bit more. So first of all, you realize that this is, like I said earlier, right? This is a challenge of quantum error correction. A whole continuum of different errors can occur. There could be erasure, there could be amplitude damping, there could be a phase flip, there could be bit flip, there could be depolarization. So the way standard error correction addresses this problem is by doing what is called general purpose error correction. Okay, which is that you discretize the errors. Hello, was there a question or? Okay, you discretize the error in terms of the Pauli error base. So what standard error correction does is it says, I know what to do if there's an X error. I know what to do if there's a Y error, and I know what to do if there's a Z error. Okay, because these are all typically perfectly correctable. Okay, but instead, if I have something like amplitude damping, I will decompose amplitude damping in terms of the XYZ error. I'm sorry, is there a question or is somebody talking?
I think somebody's microphone is switched on, unmuted, and
I see. Okay. Yeah, that's okay. Maybe I'll just continue. Anyway, I think I will have to figure out when to stop this because I've gone, I mean, I'm going much slower than I anticipated. So anyway, we'll see. I'll just stop in another 5-10 minutes, and then we can decide what to do after that. Okay, so general purpose quantum error correction aims to decompose any error model purely in terms of the Pauli. And again, this is a uniquely quantum trick because the Pauli operators, as you know, form a basis for the set of all operators on qubits. So on higher dimensional versions, there are generalized Pauli operators which form a nice error basis and all that. So I can write down, for example, the E0 and the E1 of amplitude damping in terms of XYZ operator. And then because the whole process is linear, if you look at it, the entire error correction circuit is a linear circuit, right? Because everything is linear. If I correct for independent XYZ errors, I effectively correct for any single qubit error. So this is the whole idea of standard error correction or general purpose error correction, that you don't actually care what is the underlying noise model because there can be any arbitrary noise. I simply assume that all these noise models can be written down in terms of X, Y, and Z. So I will simply pretend that I just have independent X, Y, Z errors acting on my qubits. I will design error correcting codes for that. I will design recovery processes for that. And typically these recovery processes are measuring, like I said, with the ancillas and applying an X gate or a Z gate. depending on where the error occurred, and that is how I'm going to proceed. But it turns out that this approach is somewhat costly, as you can imagine, because this says that okay, first of all, it leads to an elegant structure, and this is the whole, idea of stabilizer codes. Again, I'll not have time to get into the details of this. The whole Pauli group structure leads to the idea of stabilizer codes, and this is a very beautiful mathematical theory based on the nice group theoretic properties that this Pauli group satisfies, right? But what it says is that the shortest quantum code has to be at least 5 qubits long, okay? However, in the early days of quantum error correction, people actually came up with what is called a 4-qubit code, okay? So this is what I will talk about in the next slide. I will talk about a 4-qubit code for amplitude damping, which actually performs almost as well as the 5-qubit code. And I will explain what this fidelity is, right? Again, in a slide or two. So this is how I want to motivate the idea of noise adapted QEC, that you move away from this mode of general purpose QEC. You actually care about what is the underlying noise model. You don't simply look at it as one of the Pauli errors, and then you try to design error correcting schemes for that, okay? So this is an example of a 4-qubit code that corrects for single qubit amplitude damping error. So here you see, it is not as simple as the 3-qubit repetition code. I instead have 4 qubits. This is my 0 logical. This is the 1 logical. Of course, these are also nice entangled states, right? So this is encoding 1 qubit in 4 physical qubits. Of course, there is a unitary way of doing it. I call it an isometry because in a technical sense, I'm going from 1 qubit space to 4 qubit space, right? But this is the encoding circuit. As you can see, it's not much more complex than the 3-qubit code circuit, right? And this again circumvents no cloning theorem. It uses ancillas, entangling unitaries, all of that remains the same. And it turns out, interestingly, what you can show is the same property that you had for the 3-qubit code actually can carry over for this 4-qubit code with specifics to amplitude damping errors. So the E0 and the E1 can actually be distinguished, right, and corrected up to a certain order in the noise parameter gamma. And you realize that actually what you care about is only the second order in gamma, because even a perfect, so-called perfect error correcting code, like the 3-qubit code, could only deal with the single qubit error, right? And those errors are all order P. It cannot actually deal with order P squared errors. So similarly, I can now tailor make an error correcting code for amplitude damping, which can correct all the order gamma errors and leave the order gamma squared and higher order errors uncorrected. But we always assume that gamma again is much smaller than half, and then it achieves the same degree of protection that a regular general purpose error correcting code will do. So what standard error correction tells us is that for amplitude damping, you need at least 5 qubits. The 3-qubit was okay if you just assume that you had only bit flip noise, right? But if you assume any kind of noise like amplitude damping, you need at least 5 qubits. But what this paper showed in the 90s, even in the late 90s, is that there exists a 4-qubit code which can actually correct for amplitude damping errors up to the same order in the noise. Okay, so the rest of this talk is essentially going to be about these kind of noise adapted error correcting codes and how to construct them, how to actually design circuits for them in such a way that they can be implemented fault tolerant. So maybe, so is Prashanta here? So I guess you have another talk now at 11 o'clock, is that right?
Yes, Prabha. Another talk at 11.
Correct. So then maybe what I will do is I will just take 5 more minutes and quickly run through the main results, right? The other possibilities, I don't know if there is room to continue this talk. You know, let's say I'm about halfway through the talk, right? So maybe the organizers are here. If I can continue this at a later day and time, then I'm happy to do so also, okay? But for now, I will quickly run through the results that we have relating to these kind of noise adapted codes. Okay. All right. So this is all some more technical stuff, but this is what I wanted to show you. So when I talk about these approximate codes or noise adapted codes, then how do I actually compare different error correction procedures, or how do I say that the 4-qubit code is doing as well as the 5-qubit code and so on? The way I say it is using this metric, and this metric is what is called the worst case fidelity. Okay, it compares. So what you see here is actually a simple overlap function, right? What I have inside here is the action of noise followed by recovery on a particular state. And then I take the overlap of that. This is the final state, you see. I take the overlap of that with the initial state. This is what is called the fidelity. I say worst case because I minimize this over all states in the code space. Why do I do that? Because there are certain states in the code space which may be preserved better, and there may be certain states in the code space which actually behave very badly under the noise. In the case of amplitude damping, for example, we already saw that the Ket0 is well preserved by the noise, but Ket1 is badly affected. So an intermediate state would be a plus state, for example, the 0 plus 1 by root 2 would be somewhere in the middle. But what I want with this kind of approximate error correction or noise adapted error correction is a guarantee that no matter what superposition I have in my computation, no matter what superposition I prepare, I will always achieve a certain minimum fidelity. And that is what the guarantee that the worst case fidelity provides. So this is now the comparison. I have the bare qubit, which is the qubit without any quantum error correction. That achieves a fidelity which goes as 1 minus gamma. The 4-qubit code achieves a fidelity of 1 minus 2 times gamma squared. And I showed you a couple of slides ago that the 5-qubit code also achieves 1 minus 2.5 gamma squared. So you see the 5-qubit code achieves almost the same fidelity as the 4-qubit code, but now the 4-qubit code can be done with fewer number of qubits and fewer number of gates. So this is the advantage of noise adapted or approximate error correction, that you can continue to preserve quantum states with high fidelity, but by making reasonable assumptions about the noise, you can actually bring down the number of resources that you need for doing this. So the first piece of work that I wanted to present was how do you construct such noise adapted codes? I just showed you one example, but that was an example that people worked out using some analytical properties of amplitude damping noise. But in general, I could have an arbitrary noise model. So how do I construct? So I will not have time to go through the details of this. So I will refer you to this paper first of all. This is a paper written with my collaborator Hui Kun and 2 of my students, Angela and Akshaya. So this paper tells you how you can systematically search for good quantum code for specific noise models, which are not Pauli, which are not of any particular structure, but all you know is these Krauss operators of the map. Then how can you construct an error correcting procedure for that? So that is what this paper tells you. I'll quickly go to the summary of this. That what we do in this paper is to present a simple and fast numerical procedure to search for good quantum code. And we show the key thing that we use in this paper is a very nice algebraic tool called the Cartan decomposition. Okay, and I encourage you to look up the paper to see how we use this, make use of this Cartan decomposition, which again invokes properties of Pauli operators and so on, right? So this was the first piece of work that I wanted to talk about. Maybe I'll just show you the results here. So this again is a comparison of the fidelity in terms of how well the fidelity, how does the fidelity drop as your noise parameter increases, right? So what's on the x-axis is the noise parameter. So you see the red line is the no error correction line. And this line is falling linearly as a function of the damping parameter. So this is falling very fast. But all of these other lines are error corrected fidelity plots. But you notice that this dash dot line, right, is the 4-qubit code, the example that I showed you. Okay. And the 5-qubit code is here, the solid blue line. but the numerical codes that we construct, which is the black line and the pink line, actually fall off even slower than the perfect 5-qubit code and the approximate 4-qubit code. So this tells you that maybe there is advantage in actually optimizing the quantum error correcting code to the particular noise model that one is looking at. So in this case, it was again amplitude damping noise. But what the pink and the black line show is that the numerically optimized codes actually give you better fidelity than the perfect 5-qubit code and the approximate 4-qubit code. Okay. So I will just conclude by mentioning the second part which I wanted to talk about, which is fault tolerance. So as I said, in quantum error correction so far, we assume that all the processes are perfect, right? So there is ideal gate operations, perfect state preparations, and perfect measurements. But the question is, are these QEC protocols really effective when you have faulty gates, when you have faulty preparations and faulty measurements? And what fault tolerance aims to address is it provides a framework such that you can construct faultless or noise resilient quantum circuits, even though the basic building blocks are all faulty, right? So it allows for reliable computation with noisy quantum states and faulty quantum gates, provided the noise is below a certain threshold value. So I don't think I will have time to get into the details of this, but once again, I may quickly show you my final summary slide, which says what was our contribution in this. So I will quickly jump to that. Okay. Yeah. So what we show is you can tailor this kind of a fault tolerance scheme, again, to amplitude damping noise using something which is as small as a 4-qubit code. Okay. And the kind of circuits that we construct, and this is again something that I already emphasized in the early part of my talk, you need non-trivial recovery units, unlike the Pauli noise case, where you simply do an X operation or a Z operation or a Y operation. That's all your recovery is. But in this case, you have to do non-trivial recovery, which is different from a simple Pauli operation. This Pauli operation is technically called a Pauli frame change, okay, in this literature. I will not have time to tell you about noise structure preserving gates, so we'll skip that. But I just want to say that our work tells you that it is possible to do fault tolerance, achieve fault tolerance using very, I mean, the circuits are not very simple, but the kind of resource requirement is smaller than, say, the kind of codes that one needs today, like the surface codes and so on, which require hundreds of qubits actually to achieve fault tolerance. Okay. So let me stop here. And I'm sorry that I could not really get into the technical parts of my own work, but hopefully I gave you an overview of quantum error correction and told you a little bit about fault tolerance. So I'll stop here and take questions if there are any.
Thank you, Prabha, for the nice talk. So before the questions, there is a request from the organizers that if you can continue, give a second part of the talk.
Okay.
As you wanted. They haven't specified a schedule, but maybe that they can discuss with you, I guess.
Yeah, sure. We can discuss that over email. And so the second part will basically, I can get into some more details about fault tolerance and. Okay, shall we do this over email? Yeah, okay. Yeah, you're welcome. Do we have time for questions now, or we can just?
Yeah, we can take a few questions now. Yeah.
Okay.
So guys, if you have any question, please feel free to ask.
Okay, so I don't see any questions.
I think there are no questions, I guess. So, okay. Okay, just a minute. There's a question on the chat box. I don't know. I didn't know the question is not even complete. Okay.
Yeah.
So anyway, thank you very much for the nice talk, Professor Prabha. And we hope to see you in one more talk soon, I guess.
All right. Sure. We'll do that. Yeah.
Yeah. And thank you very much for joining us.
Yeah.